To take the derivative of the function f of x equals secant of x to the x power, since we have both the x in the base and in the exponent, a logarithm is going to be required for this derivative. And so we use the process of logarithmic differentiation as the way to take this derivative so that we can introduce the logarithm. So what we do for logarithmic differentiation is we start by rewriting. So we rewrite so that we have y equals secant of x to the x power. Then we natural log both sides, so ln both sides. This is the way all logarithmic differentiation problems start. So once we've natural logged both sides, we've got natural log of y on the left-hand side, and we do that to balance the natural log that we really need on the right-hand side, secant of x to the x. So the reason that we needed that natural log on the right-hand side is so that we can use our algebra rules to bring down the x. So the natural log of y is equal to x natural log of secant of x. And so since we had x in both the base and in the exponent, when we bring that exponent down front, what we create is a problem where we need the product rule to be able to find the derivative. So we're ready for the derivative now. So we'll continue in the next column. To take the derivative, we'll do it term by term. So we've got y prime over y on the left-hand side, and the right-hand side we've got a product rule. So filling out the product rule, we've got the derivative of the first, which is the derivative of x times the second, natural log of secant of x, plus the first term, which is x, times the derivative of the second, which is the derivative of natural log of secant of x. So we'll take these little derivatives inside the product rule to continue. So we've got y prime over y is equal to the derivative of x is 1 times natural log of secant of x. And then we have plus x times the derivative of natural log of secant of x. So the thing that we're trying to take the derivative of here is a natural log of something ugly. So it's going to require the chain rule where the input of the logarithm lands on the bottom. So we've got secant of x is landing on the bottom, but its derivative, we pull out its derivative, and I'm just going to go ahead and put it on top instead of multiplying it beside it. Its derivative, dy or d dx of secant of x, lands on the top there. So we have one more derivative to take here. So we have y prime over y is equal to natural log of secant of x plus x times, we've got the fraction where secant of x is on the bottom, and we've got the derivative of secant of x on the top. And so these trig derivatives are also pretty new here. So the derivative of secant of x is secant of x tangent of x. And that's just a derivative you either need to know or know how to derive from some other information. So to clean up just a bit more there, we see that we have a fraction with secant of x on both the top and the bottom. So that secant of x is going to cancel, leaving you just with the x that's out front here times tangent of x for our second term in the sum. So to finish off the problem, we need to isolate the y prime. So we've got y prime. Well, let's see. What we're doing here is the step that we always do. We multiply over the y. So we multiply the y over. So we multiply both sides by y, leaving us with y prime on the left-hand side is equal to y times, and you need the parentheses here because it's multiple terms added, natural log of secant of x plus x tangent of x. And the final step then is just to put back our notation. So we've got f prime of x is equal to, and we don't want y in our final answer. We know what y is. Y is secant of x raised to the x power, and then we've got all of it multiplied by the natural log of secant of x plus x tangent of x to complete our derivative. And so this was an example where logarithmic differentiation was being used and really very necessary because x was in the base and in the exponent.